This is Hinata, and she wants to learn about quantum mechanics. Quantum mechanics is a fundamental theory in physics that describes the behavior of nature at and below the scale of atoms, a theory that governs the fundamental building blocks of our universe. To understand the fundamental nature of our reality, we need to understand the physics of these particles. When a ball comes flying towards you, keeping in mind the environment, you're able to predict where it is going to land. This is classical mechanics at play. Our brains are wired to predict the predictable. However, the object of study of quantum mechanics, electrons, photons, etc., are so small to see, even with best optical microscope, and our eyes and microscope are sensitive to visible spectrum of light, whose wavelength itself is few 1,000 times longer than the size of the atom. In this incredibly small realm, our intuition fails us. Understanding these particles requires a flexible mindset to accept surprising facts and realities. Only then we can move forward and learn something useful about them. In classical mechanics, if we know the state of a particle, we can use the laws of physics to predict how the system evolves. This is not the case in quantum mechanics. In classical mechanics, the state of a particle includes both its position and momentum, and these two quantities are independent of each other. We can measure them independently. In quantum mechanics, position and momentum don't have definite values but are observables as proposed by Heisenberg. They only exist when measured. The question, what is the position of the electron, has no answer before you ask it. We can only calculate the probability of observing different values upon measurement. Position and momentum are not independent in quantum mechanics. One cannot know the position and momentum of a particle simultaneously. The main catch is that measuring and observing in quantum mechanics has a profound meaning and isn't the same as measuring a classical system. As you know, in classical mechanics, measuring an object's properties, like its position and momentum, doesn't change those properties. The act of measurement is passive, it doesn't interfere with the system. For example, using delicate instruments, we can measure a planet's position without significantly affecting its orbit. Just the mere act of looking at a physical system has a profound role in the system's evolution. Inspired by our classical intuitions, we have analogies like this when we look at the positions of planets in the sky or billiard balls on a table. Our vision involves photons, tiny particles of light hitting the objects and bouncing back to our eyes. These photons carry a small amount of momentum, which can slightly alter the object's path. However, these analogies only help to some extent and don't fully explain what's happening in quantum mechanics. The effect of observation in quantum mechanics is much more profound and complex than in classical physics. In quantum mechanics, measurement is a type of physical interaction, just like in classical mechanics. However, unlike classical mechanics, where we can minimize the interaction's impact, even the tiniest measurement in quantum mechanics can significantly change the system state. The central idea of quantum mechanics is that what actually exists in the quantum world is not the same as what we observe. Our observations only give us part of the picture, and the act of observing itself changes the system. This experiment shows that particles such as photons and electrons can exhibit both wave-like and particle-like properties. When particles pass through two closely spaced slits and are then detected on a screen, they create an interference pattern characteristic of waves. However, if one observes which slit the particle passes through, it behaves like a particle, and the interference pattern disappears. If we put a detector that measures the electron as it goes through the slits, the electron's wave function will collapse onto either going through the left slit or going through the right slit. This experiment is fundamental in understanding the wave-particle duality in quantum mechanics. However, the good news is that we do have a tool to know about the evolution of quantum system, the Schrödinger equation. The wave functions obey the Schrödinger equation only until they are observed. Once an observation is made, the wave function collapses immediately, irreversibly, and indeterministically, and the Schrödinger equation is no longer relevant. Yes, it is. Even the mathematical abstraction of quantum mechanics is quite different from classical mechanics. The space of all states in classical mechanics is a set and follows Boolean logic. However, the space of all states in quantum mechanics is not merely a set, but a vector space and follows different logic. For example, in the classical world, the basic unit of information is a bit, which can take only two values and take only one value at a time. However, a qubit quantum bit can exist in a superposed state of 0 and 1. That is, it can assume both values 0 and 1 simultaneously. What we have discussed so far is just to give you an overview of quantum mechanics and how it is different and counterintuitive compared to classical mechanics. Despite being strange and hard to grasp, quantum mechanics is fundamental to understanding the nature of reality. To learn quantum mechanics properly, you'll need to study it formally. This means having a background in mathematics and physics. With the right knowledge and tools, you can start to make sense of this fascinating and complex field. Excellent questions. First, the reason classical systems don't show the bizarre behavior of quantum particles is due to a concept called decoherence. In large systems, the quantum effects average out and the classical behavior emerges. And we have a classical approximation that explains our world very nicely when the object of study are sufficiently large in size. Essentially, when you have a large number of particles interacting, the quantum weirdness gets washed out, and we see the predictable, intuitive behavior of classical mechanics. Stay tuned for more videos related to quantum mechanics.